that's a phase diagram. Okay? The objective says to, or that we should be able to sketch a typical phase diagram, label all the axes, mark the significant temperatures, things like that. Objective number 14. Sketch the diagram, label the axes, significant temperatures, and the thermal processes on the diagram. Okay? I'm going to just draw this up on the board. You have it all to scale on your papers there, so you're going to look at those numbers that are on here. We're going to draw these with temperature up here in degrees Celsius. We're going to have Q down here on the horizontal axis. In this case, it's times 10 to the 4th joules. Okay. This phase diagram is based on these numbers for whatever substance this is. These diagrams and the numbers that go on the axes will be different because everything's going to have a different melting and boiling point. It will take different amounts of energy to do the different things that we'll see on the diagram. But all of your diagrams will have this shape. And so we're going to apply this to these ones with these numbers, but they will all look like this. And I'll first start by kind of just marking this up here with some of these important temperatures and the different phases. But then the numbers really only correspond to this diagram itself. These aren't true in general for the numbers. That's a 1.2 here, this last one is 1.8. And then we have a temperature here and a temperature here. So 110 and 140. Okay.
Your 0.4 should be a 0.6.
0.6, thank you. Okay, so this shows the different phases of whatever this substance is. Okay. Notice over here that we don't always start at 0. We can start anywhere we want to. We're just kind of showing the different phases here that we have. We don't know what this is, but we know we're starting down here at lower temperature. At lower temperature, what phase are you in? A solid, a liquid, or a gas?
Solid.
So this is solid down here. We're raising the temperature of a solid here in this range. That's what this graph is showing right here. The temperature is going up this way, and to do that, to raise the temperature, you have to add heat. So my heat, we're getting bigger this way. What's happening right here? Then, if I heat it up to a certain point, then it starts to melt here. The temperature's not changing, so here we have a phase change. I'm going to put LF here just because that's the LF that we're going to use, the latent heat of fusion, that will describe that phase change. It's melting if I'm going here from left to right. What phase are we in over here? This is liquid. And if I'm going here from left to right or going up this way on the graph, then we're raising the temperature if we're going that way. We're cooling it down if we go the other way. Up here we have another phase change. I'll put the LV there just to kind of show what that's going to be there. Gas or steam up there at the top in that last phase. Okay.
So are the phase changes on the graphs always leveled out like that?
Always.
Documents the...
There is no temperature change during a phase change. So during these two phases right here, phase changes right here, the temperature is constant. This whole way through, imagine this like being a chunk of ice. You're adding more and more energy into that ice to completely melt it. But all that energy is going in to melt the ice here. You don't start raising the temperature of that ice until it's all water, and then you can start heating up the water. Okay. So these are the different phases here on the diagram. The thermal processes here, the phase change here. You don't need to write down that we are changing the temperature here, here, or here. It depends on if we're going this way or this way to say if we're increasing or decreasing the temperature. I really just want you to know which phase is which. Show me where the phase changes occur. The temperature changes occur for all these lines that are having some slope because this is my temperature axis. Okay. This is 110 degrees and 140, okay. What else can we call that 110 degrees in terms of words here? Which temperature is that? We're going from a solid and then to a liquid here in this phase change. So this is the boiling point.
Right, that should be the melting point.
Yes. I was just listening and not really listening or thinking, but this is the melting point. No, that's okay. And then this is the boiling point up here. And on your phase diagrams, if I ask you to sketch a typical phase diagram and I don't tell you what it is, then you don't know what numbers go on the axes here. But you could still label this point that corresponds to this horizontal line here as the melting point, and this one up here as the boiling point. That's all you would need to say. Sometimes I just say, sketch a typical diagram, and I don't tell you what it is, and I just need you to show me this diagram, label what I have on here, label these points and words on the diagram up here on your vertical axis, label it as the temperature and the q-axis, and label your axes that way, but you just won't have any numbers on here. Okay? Now if I told you what it was, and if this was water, then what number would you put right here?
0.
That's where you look at the table. So for water, you might have these memorized, you might know them. But for anything else, if I asked you for lead, you'd look there on lead and you'd see, okay, it has a melting point of 328. And you put 328 right there. And then you'd put your boiling point of however many thousand we have up here for the melting point, the boiling point of 1744 up here at this point. Okay? The numbers down here, you would only know how much energy you need if I told you how much mass it was. So most times, at the most, if I tell you what it is, that would tell you what numbers to put on the temperature axis. But down here, how long these lines are, how steep they are, really does depend on what mass it is and how much mass and what it is to tell you how steep these would be. But I don't care about the scale of these, how steep the lines are, how long these things are here, unless I actually gave you numbers to calculate. And for the diagrams, I don't do that. Okay? You would just be expected to be able to put the correct melting and boiling points on here, and the scale down here won't matter. Just label it as Q, label it as your T, and if I don't tell you what it is, you just call this the melting point and the boiling point. Label all these pieces in the graph here. Okay? Now, for the problem that I've given you, we have numbers, we're going to calculate some things based on the diagram. But this is what a typical phase diagram would look like. Now we'll use our numbers here for this problem to solve for whatever we need. Okay? But that's what I'm looking for a phase diagram. Anytime you have a problem that you're going to solve for something that involves a phase change, like melting ice, draw a phase diagram. It's very easy to forget, like I told you before. If we had ice that started at -5 and was in a cup of water that ended up at room temperature, we would be starting down here, raising the temperature to this melting point, melting all the ice, and then raising it up to somewhere in here in room temperature. Each different piece on the diagram here is a different Q. And so that ice could have 3 different Qs. The Q for warming it up to its melting point, the Q for melting it, and then the Q for warming it up again to its room temperature, whatever it would be. That would be a piece here, this piece here, and another piece there. And if you draw this, this will really help you maybe remember to think about all the different possible Qs you might have for just that one mass there for the ice. Okay? So anytime I have a phase change, I need to be thinking about, am I already at this point right here at this temperature? And if I am, then I can change the phase. If I'm not, I need to either warm it up or cool it down to get to the point right here where we're able to change the phase. You can't change the phase unless you're at that point or at that point right there. And that's why sometimes these diagrams will be really useful to make sure you're accounting for all the different energies that you have. Okay? For this problem, we're going to solve for the C's, the specific heats, and the latent heats everywhere. I think part of it was already, let's figure out what the melting point and the boiling point is. We've already marked that on our diagram. Was that part A? For the melting and the boiling point? Okay. And then the next parts, B and C, I think are just going to be, let's find all these C's and L's. I'm just going to label these C1, C2, and C3. And I've already called this LF and LV. we're gonna assume that when we're going through this, we're gonna kind of move from left to right as we're going through, but it doesn't really matter which way we go. It would affect the signs of the Q's in here though. Remember, these Q's, these parts of the graph here, all correspond to which one of the Q's up here? The sloped part of the graphs there correspond to which Q? The top one, because those are the ones where we have a temperature change if we're going up at all, okay? These Q's here correspond to your phase changes, the Q's that are equal to ML. These Q's, we can get the sign of that Q by just doing our delta T in the correct order. These Q's we need to think about. We need to choose those signs on our own. I didn't write down them yet, but I wrote down that it was energy lost or gained, added to or removed from the system early on with the plus or minus signs. We can also see here though that if I'm going this way with my Q, then we have positive Q. And if I'm going this way on the graph, I have negative Q. So you can memorize if you want to that a solid to liquid phase change would be what sign? Positive. And you can write these down. Solid to liquid is positive Q. A liquid to a solid is negative Q. And that probably makes sense when you're thinking about, well, if I'm going from solid to liquid, I need to add some energy to it to think about maybe melting that ice. Okay? Liquid to solid, that might not be so obvious. When you say you're melting or you're making ice, you might not really be thinking, well, where's the energy going? It's easier, I think, to think about when you're melting it. When you're melting that, or when you're freezing the ice, you're removing energy from the water to freeze it, but that may not be as intuitive as melting something, okay? So these you can just memorize, but if you also remember the diagram here, these are very easy to just say, well, it's positive if I'm going that way, negative this way. So then I could say if I'm going from a liquid to a gas, it's positive Q, from a gas to a liquid, negative Q. Memorize these if you want to, or just look on your diagram and remember those sign conventions here, what kind of the direction that you're moving on the diagram. Yeah?
What about like a solid to a gas, like dry ice?
What about a solid to a gas? From here to there, you're still going to the right, it's still positive. There are little differences though with dry ice that we won't get into, but here with these Q's and memorizing these or knowing them from the phase diagram, just make sure you know those, because if I start putting all these Q's into an equation where we add them all up and sum those Q's to 0, then if I don't choose the correct sign here, then we might get the wrong answer, okay, depending on how many Q's we have. Okay, so we can see that from our diagram now. We can get all the different C's that go with these ones in green here. Those would correspond to this kind of Q. So if we're going to do that for, let's just start with the solid phase, that part of the graph has a Q1, which is equal to MC1 delta T. And we can call it delta T1 if we want to. But we're just going to do MC delta T for each of those 3 parts, and then we're going to do the phase change Q for these 2 other places in the graph. Okay. We said here is 1 kilogram, right? Yeah. So it's 1 kilogram. We know the temperature change, and the Q we can get from the graph. Okay. The Q, remember I was saying before, we don't just have Q at one point. So these are marked at points on your graph. But I can't say the Q at a temperature of 110 is 0.6 or 0.4. There's only an energy change or a transfer of energy. So the energy that it takes to go from one point to another point on the graph would be measured down here this way. But I can't just say this point right here has a Q of something right here. It doesn't work that way with Q. Remember, it's an energy transfer, so it's not just a single state variable right there at that point. Okay? So the Q, we never write as a delta, but you can really be thinking of it like a delta, because it's an energy transfer that corresponds to the change in temperatures. Okay? So for this first part here, what's my temperature change?
It's 110.
How much? 10, because we start down here at 100. So my delta T is 10 degrees there. What's my Q there? Point one. From down here times 10 to the fourth, because we have that there. And this actually started not at 0, but 0.1 down here. Or each of the little boxes is 0.1 down there on. That would feel like 0, but notice there you've got each box being 0.1 down here on this Q axis. So you have your Q, which is 0.1 times 10 to the fourth joules over the 1 kilogram, and then the delta T of, is at 10 degrees Celsius for the C1 there. Is that right for all of our numbers there? 0.1. And this just gives me 100 joules per kilogram per degree Celsius for the C1.
I have a question. Is it 0.1 for the Q1 because that was the difference between the 0.1 and the 0.2?
The energy that it takes to go from here to here is this amount in between here and here.
Okay.
Yeah. And that's why I was saying, it doesn't get written as a delta, but when you're thinking about it like this in terms of the points on here on the axis, it's the amount of energy that it takes to go from here to here. So how much energy in between there. Yeah. And then we just keep doing this for all the other points. I'm going to do parts B and C together. I'm just going to kind of move from left to right on the diagram here, and we'll do C's and then the L's just kind of in order here. So now let's do the phase change. That is next there. We're going to have a Q is equal to N times LF for that first one here, the late heat of fusion. That's what we're going to solve for here. So the Q over the N here would give us how much? Well, what's our Q here for the phase change?
Is it 0.4?
0.4 times the 10 to the fourth joules over the 1 kilogram. I'm just keeping the 1 kilogram everywhere to make sure we keep our units consistent. And this is just the 4 times 10 to the third joules per kilogram for the LF. You guys seen how that works? And then you would do the exact same thing for all the other points. I'll go ahead and do it for the next one also. So for that liquid, you'll do the Q, which we call 2 up there, and C2 delta T2. We'll do the same thing now. The Q here is going to be, what is that there, 1.6, from 0.6 to 1.2, 0.6 times 10 to the fourth joules divided by the kilogram. And then our temperature difference there goes from the 110 up to the 140, so 30 degrees Celsius there to give us that delta T. Is that clear on where I get the delta T's from and the Q's? And so here we get 200 joules per kilogram per degree Celsius. And then the next phase change here would give us LV, which is 6 times 10 to the third joules per kilogram. And then we can get the C3 at the end there to be 100 joules per kilogram per degree Celsius. I'll just leave those for you to fill in if you want to, but they're the exact same calculations as we did over here, just different numbers that you'll read from the graphs. You all okay with me leaving those couple lines off over here for these numbers? You all know how to get those? you should be able to draw these on your own, you should be able to read and interpret them, maybe do some calculations like this. You should understand these diagrams and what they represent. And these were all just, I think, simple calculations as long as you know how to interpret the Q's and the delta T's. Know where to get those from the graph. Yeah.
Is the mass always 1 kilogram for these?
For this
these-
problem it was.
Okay.
Because we just said 1 kilogram.
Did we just assign that number, or where?
No, the problem did.
Okay.
The first 2 words.
Okay, I see.
Yeah.
Okay.
It's easy to miss there because it's not written as a number with the kilograms, but yeah, we'll have to tell you what mass it is, otherwise you wouldn't be able to figure out what these are.
Okay.
It would take more energy if I had a bigger mass here, and so all these numbers would be different. But that's something that was just easy here because it was 1, but it could have been anything.
Mm-hmm.